Testing, 1, 2, 3, testing. All right. This is the video response to InRem that I promised I would produce for him today. And so this is it. What we have here is a GeoGebra 3D model. It's not to scale. I can make it to scale at the end of the video, and we'll see that it still works the same way. It's not to scale simply because this way I can have the Earth and the sun visible at the same time, and I don't need to zoom in forever to actually see detail on the Earth. We have the sun being a sphere at the center of all the axes, a sphere with a radius of 4 units. Out 25 units away from the center of the sun, I have the Earth. The Earth is a sphere 1 unit in size. And there's a lot going on the sphere of the Earth, so I want to show what all these things are. So we're going to look at the Earth head on. Okay. So this dotted line here, this is the plane of the Earth's rotation around the sun. Okay. This red line here, this red circle around the outside of the Earth, is the Earth's equator. And the Earth's equator here is tilted 23.4 degrees off of its orbital plane. Because in the heliocentric model, we know that the Earth is tilted 23.4 degrees off of a straight up and down axis. Good evening, Shrumanati, and good evening, Terman. So we have this point G on the equator. Point G on the equator. And we can move G, assuming we can click on G. There we go. We can move G around the equator if we want. Okay. We also have, let me spin him back around. We also have a point J. So basically, I have a line that goes from G up to the North Pole. Yeah, let me show you the poles, by the way. So because we have the equator here tilted 23.4 degrees, we also have the North Pole and the South Pole, again, tilted 23.4 degrees. This gray dashed line represents the direction to the star Polaris, the North Star. It is, for all intents and purposes, directly above the North Pole. So a person standing up here at the North Pole would look straight up, 90 degrees up, to see Polaris. There's one more line on the Earth. It's this black circle. This black circle represents the terminator line. The terminator line is the line between sunlight and daylight. So I can show you. Let me move the Earth around a little bit. Oops. There we go. Okay, so if I move the Earth around in its orbit, the terminator line continues to represent where the light of the sun stops reaching the Earth. So you can see here the terminator line is here. So that means this side of the Earth is in sunlight, and this side of the Earth is not in sunlight. And if I move the Earth over to here, we can now see this side of the Earth is in sunlight, and this side of the Earth is not in sunlight. You have to be on the dark side of the Earth in order to see Polaris. So you need to be behind the terminator line. You need to be on this side of the Earth to see Polaris. So if we zoom in again, okay, let's zoom in a little more on the Earth. Okay. So again, the red line is the equator, and I have this angle measurement here. What this is, let me bring G over here. Okay, so G is a point on the equator, and I have a curved line, an arc from point G on the equator up to the North Pole. Hi, Baryon. And then I have a point J, which is somewhere along the arc from the equator to the North Pole. And I can move J around. I can move J to any latitude north of the equator that I want. And his latitude north of the equator is represented by this angle alpha. You can see this angle being measured here. Basically, this angle between J, the center of the Earth, and G, that angle represents the latitude of the observer at point J. And then I have this yellowish green line. It's another circle, and that just represents the line of latitude on which J is located. Okay, so J can be down close to the equator, or he can be all the way up right by the North Pole. Okay, so again, we see that this angle tells you the latitude of J. You'll also notice another angle called beta. And if you look closely, you will see that angle alpha, which right now is, let's put it right here. Angle alpha right now is 23.366555581 degrees. And you'll notice that angle beta is also 23.366555581 degrees. Okay. And you'll notice that angle, those two angles, alpha and beta, remain exactly the same no matter where I put J on the surface of the Earth. No matter what line of latitude north of the equator J is at, his latitude is the same angle measurement. Oh, hang on, phone's ringing. All right, sorry about that interruption. We're back. So I was basically explaining, I think, that anywhere I put the observer J, his latitude is equal to the angle that he has to look above his horizon to see Polaris. And so that brings us to the two last lines that I want to show you. This light blue dashed line is the horizon for the observer at J. And this horizon line is a tangent to the surface of the Earth. So basically, if there was a guy standing at J, the horizon line is perpendicular to him, and he's perpendicular to his horizon because he's standing up. And the last line is the dark blue dotted line. And the dark blue dotted line represents the observer's line of sight. Hey, Jesse, thanks for stopping by. The dark blue dotted line represents the observer's line of sight to Polaris. And again, what we'll notice, first of all, is that the observer's line of sight to Polaris is parallel to the axis of the Earth. Another way we could phrase this is, no matter where on Earth the observer is, his line of sight to Polaris is parallel to any other observer's line of sight to Polaris. So if I wanted to, I could put another observer along this arc, and his line of sight to Polaris, hi near base, his line of sight to Polaris would be parallel both to the axis of the Earth and to the line of sight to Polaris of my first observer. Okay, but now we have to notice our observer J right now is on this side of the terminator line. Yeah, Jesse, I'm sorry to be broadcasting right when Sean was. I just saw that he was doing his live stream, and I'm not expecting to sap viewers away from him. His live stream doesn't use a 3D model. As far as I understand, his live stream is a drone that is capturing multiple sunsets by increasing its elevation. So you guys should definitely, if you want to keep watching this, please do. After you're done watching this, go over to Sean Hufford's stream, and you can watch multiple sunsets. You can be like the Little Prince on his planet. You know, Little Prince was able to see multiple sunsets in a day, not by increasing his elevation, actually, but by going around his planet. Anyway, all right. Well, you guys can all catch the replay when I'm done here. Okay. So like I was saying, clouds, that sucks. So like I was saying, on this side of the Earth, on this side of the terminator line, we are in sunlight, and the light of the sun scatters in our atmosphere and makes our sky look blue, and we cannot see the light from Polaris. The light from Polaris is too dim to overpower at the distance it is from us. The light from Polaris is too dim to overpower the sunlight and the blue of the atmosphere. But if I rotate my Earth a little bit, if I move G to the other side of the terminator line, okay, now the terminator line, you see the terminator line? Okay, now we're on the dark side of the Earth. Okay, now J is able to see Polaris. And you'll notice that his line of sight to Polaris, the angle that he looks above the horizon, is still the same as his latitude. It's still, in this case, 39.75879258888. No matter what altitude, no matter what latitude he's at, his angle to Polaris is the same. No matter what time of day it is, no matter where the Earth is in its rotation, and no matter where Earth is in its orbit around the sun. Okay, so I could move the Earth. Oops, I could give myself a headache. I could move the Earth, you know, like, oops. I could move the Earth if I could actually move the Earth, if this would work properly. I could move the Earth all the way over here. So this is like 6 months later on our model. And so long as I put my observer on the other side of the terminator line, there we go. Okay. So now the observer is in the nighttime, and his line of sight to Polaris still equal to his latitude, still parallel to the axis of the Earth. Now, the reason he can see Polaris in his nighttime sky is because the light from the sun is not reaching his eyes. If the light from the sun reached his eyes, it would be too bright for him to observe Polaris. But because the light from the sun that goes past the Earth doesn't come back to the Earth unless it reflects off of something in the sky, in the heavens, in space. And because the light from the sun that travels past the Earth is not itself visible, okay, in REM, I will scale the distance. When I'm done with this small demonstration, I will scale the distance, and you will see it doesn't change what I'm showing here. But the light from the sun that's going past the Earth, we can't see it in space. The only way we can see the sunlight in space is if it reflects off of something and comes back to our eyes. On the dark side of the Earth over here, my observer over here, come on, my observer, who is now not playing nice. Okay, so my observer on the dark side of the Earth, because he's on the dark side of the Earth, he cannot see the light from the sun that's whizzing past him. He just won't see it. And because he won't see it, it will not interfere with his vision of Polaris. Now, I'm pretty sure that's all I wanted to demonstrate with this model here. What I'm going to do now is I'm going to scale everything properly. I'm going to divide all of these numbers by 1,000. So instead of making the sun a radius of 432,000 miles, I'll make the sun a radius of 432 miles. Okay. So we're going to make the sun a sphere of 432 miles. And instantly it's bigger than we can see. Where did it go? Where did the sun go? What did I do to the sun? Hang on. Yikes. Come on. I do not know what just happened here. There we go. Okay. So let me zoom out here. Let me see if the sun, yep. Okay. So there's the sun. We're inside the sun right now. Don't freak out. So we have the circle. Oh, is the sun all the way down here now? Yeah. Okay. So the sun's all the way down there. All right. The next sphere is going to have a radius of 3.959. That's the radius of the Earth divided by 1,000. And we need to make the circle, the orbit of the Earth, not 25, but 93,000. All right. So now let's zoom out and just keep zooming. So this is going to be a to scale model. Every unit is 1,000 miles. Okay. I'm going to hide the axes because they're kind of getting in the way of seeing things. Okay. So that's the sun. Okay. This is the sun over here. This is the Earth in its orbit. I'm going to zoom in on the Earth and its orbit. Got to keep zooming in quite a bit because, oops, because the Earth is much, much smaller than the sun. And now the lines are not showing up. All right. I apologize to you in REM. When I resized the Earth, all of my figures on it. Okay. See, for some reason, the pole line disappears when I zoom in. Oh, okay. The pole line is still there now. But all these figures, which are supposed to be on the outside of the Earth, are not. Let me see if I can correct those. Hang on. Circle with center B and radius 3.959. Okay. I fixed the equator. That's okay. While you have the Earth move to 45 and look at the sun. INREM, I'm doing Polaris right now. When I'm done resizing everything and we've looked at Polaris again, then I will move to 45 and look at the sun for you, okay? Let me make all these circles work properly. Yes, Barry on. By the way, I kind of randomly and casually calculated Polaris's parallax in a reply that I was going to give in REM, but it ended up not being relevant to what the two of us were talking about. So I ended up not posting it. But yeah, I measured Polaris's parallax just using a simple triangle of 186 million miles for the base and what was it, 422 light years for the hypotenuse, the distance. I guess it was 93 million miles for the base and 432 light years for the hypotenuse. And I got a parallax that was within the plus minus that Wikipedia says for the parallax for Polaris. So I was thrilled that I was able to do that. Okay, so I think we're good here. We're almost good here. There's a couple more things that are not showing up. Uh-oh. Yeah, I'm sorry, INREM. It's not working 100%. When I scaled it up, it's missing some of the features that are supposed to exist on the Earth. So what I will do another video in a couple days. And I will do it at the proper scale to begin with so that I don't have these problems when I change the size of everything. But now, like you requested, let's put an observer at 45 degrees. I'm going to undo a whole bunch of these changes. Okay. You know, I'm just going to reload the page. Okay. So now INREM has requested that we put our observer at the 45th degree of latitude. .45-degree latitude. Come on. Wow, why is it jumping from... That's not cool. Why is it jumping from 44 to 46 like that? Okay, so now our observer is at essentially 45 degrees latitude. Okay? Our observer is at 45 degrees latitude. Let's just zoom out a little bit. You can see more or less where he is during the year. There he is. Okay. Globe to June. So June would be over here, I guess. Yeah, because the tilt of the Earth should be towards the sun. Let's swing him around to the daytime. Okay. So now our observer, it looks like our observer is pretty much right about at noon. He's almost exactly at noon. Let's see if I can get him at noon. Okay. Our observer is pretty much at noon at 45 degrees on the summer solstice. Okay, midnight. Okay. Midnight, he's now over here. Okay. Yeah, so he's pretty much, whoa, that sun is huge. Okay. So our observer is pretty much at midnight, right about there. Okay. So our observer is at midnight. So he's on the dark side of the Earth. He's at 45 degrees latitude. It is midnight for him. He's directly opposite the sun. And you can see that he is, in fact, still on the right-hand side now of the terminator line. So he is in the dark part of the Earth. He might just barely see a little bit of light on the horizon. I'm not sure for... No, the sun is not visible to him. The sun is... He's on the other side of the terminator line. He's on the other side of the terminator line. He's in the shadow. See, you can see the top of the Earth is above him. You can see the top of the Earth is above him. He can't see the sun. The Earth is in his way. See, if I go flat, if I go level, he would have to be standing right here to see the sun. He is standing behind the terminator line. He can't see the sun in REM. He would need to be above 66.3 degrees in order to be able to see the sun. He's at 45 degrees. He can't see the sun. This dashed blue line, this light blue line, represents his horizon. The sun is below his horizon. He cannot see the sun because the sun is below his horizon. He can only see things that are above his horizon. Let me move the Earth further out. Hang on a second. Let me move the Earth way far out, and let me increase the size of the sun again. Okay, so the Earth has a radius of 1 right now. I'm going to do some quick math. You guys hash this out. I just need to write some things down and do some quick math because I don't want to change the size of the Earth because when I did that, everything screwed up. So if the radius of the Earth is 1 unit, and 1 unit equals 3,959 miles, then I just need to divide everything by 3,959. So just give me a minute, okay? Hang on. In REM, the distance of the Earth from the sun means that even though the sun is huge, it won't be visible above the horizon. I'll do the math. I will make the changes, and you will see that according to the heliocentric model, at midnight, at 45 degrees latitude, on June 21st, you cannot see the sun. Okay, so if the sun's radius is that, and I divide by 3,959, I need to make the sun's radius 109.12 units. The orbit of the Earth needs to be 23490.78 units. The sun never falls below the horizon? I don't know what you're talking about, sir. All right. So the Earth is going to move out to 34490.78 units. Goodbye, Earth. And the sun is going to change its radius to 109.12 units. Now we zoom out again. Whoa. Oh, shit. I did it wrong. Sorry about that. I screwed up the sun. No, I didn't. Why is the sun looking so weird? Where are my other axes? Where is my Earth? Okay, there's my sun. Okay, there are my axes. We're zooming out to see the Earth. There's the Earth. Okay, we found the Earth, everybody. We can all be calm. We have found the Earth. So now I need to zoom in again on the Earth. When I looked at the sun from 45, the sun's edge was way above the horizon. No. When I had the camera behind the Earth, I was not standing on 45 degrees latitude. I was standing floating in space. Yeah, see. Okay. We put our observer back here at 45 degrees, essentially 45 degrees. Okay. You can see very clearly that his horizon does not let the sun come into view. I'm going to try to zoom out. There we go. Okay. See, the sun is not visible. I mean, perhaps we're having problems because of the limitations of this free graphing program that I use. Let me hide the axes. Okay, so the sun is here. Let me go back to the Earth. Hang on. Let me make sure he's on the dark side of the Earth again, because it looks like he's not. Yeah, somehow he ended up on the sunny side of the Earth again. Okay. He is now on the dark side of the Earth. It looks like he's pretty much at midnight. All right. We have the line working correct. In REM, the point is that the light doesn't stop. The point is that the light isn't visible because it doesn't reach your eyes. This is an issue that we've had. You haven't really answered my question when I've asked you, which is, do you think light illuminates a vacuum, or do you think that light passes through a vacuum? This is, as far as I'm aware, our major point of contention. Okay, here we go. We have the Earth. We have an observer at 45 degrees latitude in June. At midnight, this light blue line is his horizon. The sun is here. The sun is well below his horizon. Where would he have to be in order to see the sun above his horizon? Let's zoom back into the Earth and let's make the sun visible to him again. After this is done, I'm playing Fortnite. I'm not making YouTube videos all night long. If I move our observer, J, if I move him just barely past the Terminator line, the Terminator, then if we zoom back out, he should be able to see the sun. Just barely, but he should be able to see the sun. Can he? No, I didn't get it. I didn't get it far enough. Oh, come on. Come on. Stuff sucks. All right, I'm calling it a night. I don't see why this is acting up now. Come on. I'm almost calling it a night. It could not be that the Earth is a vacuum in REM. A vacuum is an empty space, and the Earth is clearly not empty. There's matter in front of me. There's air in my room. All right. Have a good night, in REM. I am going to call it now. Thank you, everybody, for watching. I don't ask for money. I can afford stuff myself. So maybe in the near future, I will buy a better 3D modeling. I'll buy a 3D modeling program so that I'm not depending on my browser's memory to do all this stuff. In REM, I'll just say this one more time. In the heliocentric model on the globe, you have to be on the side of the Earth receiving light from the sun in order to see the sun. Once you go on the side of the Earth that does not receive sunlight, you cannot see the sun. And the only way that you will see the sunlight is if it reflects off of something else and reaches your eyes. If I'm shining a flashlight over your head, you will not see the light from that flashlight unless it reflects off of something and goes into your eyes. Sometimes what that something is our atmosphere, which is why we do still see light from the sun when it has set, when it's gone below the horizon, because the light of the sun is still scattering in the atmosphere, and some of that scattered light reaches your eyes. But at midnight, at 45 degrees latitude, there is no light from the sun that is being scattered through the atmosphere to reach your eyes. The only light from the sun that you see at 45 degrees north latitude at midnight is light that has reflected off of something in space, and I would say like the moon, and goes back to your eyes. That's what it comes down to. The particles in the atmosphere do scatter light. I agree with you. The particles in the atmosphere scatter light. However, they can only scatter the light so far. At midnight, at 45 degrees north latitude, you will not see scattered light from the sun in the atmosphere reach your eyes. It's not possible. It doesn't happen. You don't observe it. My last point in REM is Polaris, as observed, does not work on a flat Earth. What flat Earth model exists where a person at the North Pole looks 90 degrees up and sees Polaris, and a person at 60 degrees looks up 60 degrees and sees Polaris, and a person at 45 degrees looks up 45 degrees and sees Polaris, and a person at 30 degrees north latitude looks up 30 degrees and sees Polaris. That does not work on a flat Earth. And with that, like I've said, I'm calling it a night. I'm going to play some Fortnite. I'm going to lose miserably. I'm going to have a fun time doing it. Hope all you guys are happy and dry and warm, or if it's warm where you are, like pleasantly cool. Okay? Have a good night.